the materials in Chapter 27, which is GC, and do a quick overview of Chapter 28, which is HPLC. And the two things are complementary to one another, so there's not foreign or new topics to look at. So last thing that we're talking about is the different types of columns that you can choose. Again, the most common type of columns that we have in GC are the ones that are the wall-coated open tubulars. This is the bulk of the market that fits in that. And then from that, you've got all the different options in terms of stationary phases, as well as hundreds of more that are not listed in this simplistic table. So just a couple of things that I want to talk about right quick, finishing up the chapter, is how the different parameters can influence the elution times or the elution values in a column. So things like the internal diameter play a role, the length of the column, what the stationary phase is, as well as the film thickness. Probably the thing that plays the least influence is what the carrier gas is. It doesn't matter if it's hydrogen or helium. Once you optimize the flow rate, it doesn't have that much of an influence on resolution. But we're going to look at a couple of different examples. This first one is looking at the film thickness and how it varies. So this separation, or these group of compounds that are being resolved, they are ran on three different columns at identical length, identical column or oven temperatures. The only thing that varies is the film thickness. So there's a 1/4 of a micron film, a 1/2 micron, and a 1 micron thickness of a film. And again, that's the thickness of this layer that's right on the surface of these columns. So you're talking about a minor component that's in the size of the volume of the column.
Don't you want that thicker though?
Say again?
If you want the station.
Well, if you get it thicker, it's going to get more retention. And that's the kind of the take-home message that you get out of these. So this last peak elutes in 4.7 minutes, 7.4 versus 13.2. So you need more retention to get better resolution in some cases. Yes, you do. But if you don't need the resolution, you will go with a thinner film thickness.
So it's like to fix that problem you're talking about a few class periods ago, where like the mobile phase, it'll kind of form like a peak almost. You know what I mean? Like inside the tube, like the middle has less resistance. You know what I mean?
It is. That's the bullet shape profile we talked about, and then we'll talk about that some more as we go on with the techniques. That the thickness of the film, though, really doesn't influence that. That has to do with the size of how big the tube is. Okay, so it has to do with this parameter. But as retention increases with these, you can see the resolution increases. So a little over 3, 3.6, up to 5. The sacrifice for resolutions at retention time. It's taking longer to do the run. So you get better separation, yes, but you've sacrificed almost a 3-fold increase in time to go from one extreme to the other. For me, this is good. I want the quick run. I want to be able to pop them through. I don't want to take that long. Here's the length of column. So there's a 15 meter, a 30 meter, and a 60 meter columns. These again are same oven temperature, same stationary phase material. It's a 1/4 micron film of polydimethylsilane. You'll look at, as you expect, the longer it's on the column, or the longer the column, the longer the time. But in terms of the resolution, you see an increase, and the increase that you see is typically with the square root of length. So I've increased the length by a factor of 4, but the resolution about doubled. So if you need to increase your resolution by a factor of 2, it's common to go a 4 times longer length. And when you go a 60 meter column, you're talking about a column that's at least going to cost $1,000. They're going to be pretty expensive. Here's just some examples of different IDs, internal diameters. So this is a standard 1/4 quarter millimeter or 250 micron. And here's the new type of columns that they're using called the fast columns. This is 100 microns, so it's 2.5 times smaller. If you look at the resolution between the peaks, it's very similar. Just look at these last pair out here. It's not that much difference in the two. But if you look in terms of the retention time, I've more than almost cut my retention time in half. So that's probably 24 minutes, and it's pretty close to being in half. Are you sacrificing some resolution? Like on these two, I can see that that's probably two separate peaks that are just really close to one another. I don't know if that's two separate peaks or not, but it's very similar. So it's pretty close in these examples. But again, time is money. Here's the compounds that we looked at on a slightly different column. So this is the separation of a wax column, a polar compound like we looked at. And this is what would happen if you ran that same series of compounds on a nonpolar column. So here's our xylenes, 5 through 6, or 4 through 6. So 4, 5, and 6 separate, the same order that we got on ours. If I ran it on the nonpolar column, their boiling points are so close together that 4 and 5 don't resolve. So you've got to choose the right stationary phase to get the separation that you need. One of the ways that we match up the retention times is with something called the retention indices, and this is also called Kovacs retention indices. And what it does is it allows you to take a group of normal alkanes, so straight chain alkanes, so octane and nonane or nonane and decane, and you plot those versus retention time, and you have an equation that allows you to calculate this RI. And what it allows you to do is to predict the retention time of an unknown. So in the early days where GC by itself was good enough to identify a compound without mass spectrometry, they would say, okay, here's the retention standard, and benzene I know should come out here at 6.44, and you'd have to see, does your compound come out at that number? And that was something that was a court ID'd or legal definition of that compound based on when it came out compared to a straight chain alkane. If you don't have a standard for it, I mean, always the best way to find out when something comes out is to inject the pure standard that you have. But if you don't have a standard, you can use the retention indices to predict where it will come out. So it works okay. The downside to this is that typically this only works for isocratic. So when you're doing this is you throw the gradient in there, the temperature gradient doesn't work so well. So it's got uses, but it's not ideal. So the last topic I want to talk about in GC is the hyphenated techniques. These are really our powerful things that give us the most information. Hyphenated techniques are where you combine two different technologies together. In this case, we're looking at GC combined with different things. Mass spec is the most powerful analytical tool that we have. Combining chromatography and mass spec is the best of both worlds. The only downside is that your compounds have to be volatile and thermally stable to run across the GC. But if they can, GCMS has the ability to quantify and identify thousands and thousands of compounds simultaneously in a single mixture. We did a project with the Noble Foundation where we were looking at 500 different things simultaneously by analyzing them on the column at once. Now the GCIR, it's not near as sensitive as a detector as mass spec, but now you can get vapor phase spectra. And we know that in IR, if you remember, gases had the real sharp peaks. They had the hyperfine splitting. So you've got a lot more interpretive information in their spectra than what you have in liquids or solids in IR. So GCMS is a valuable tool in terms of identifying things. Probably one of the up-and-coming technologies is two-dimensional GC or GC-GC. What happens now is the second dimension of the spectra is isolated and separated on a very, very fast GC separation. So you're going to run like a 50-meter column, and then at the end of that 50 meters, you're going to have a cryo trap that's going to freeze the compounds for like 10 seconds. And then after it traps them for 10 seconds, it's going to heat it up, and those are going to now load onto a second column where they're going to separate out. And the second column is going to have a different polarity associated with it. So now you're basically separating in a different dimension. When you do this, you get separations that look something like these guys. So this is GCGC of pesticides. So in one dimension, they got a 30-meter column. In the other dimension, they've got a 1.5-meter column. So they're taking time slices that are coming out of this long column, and then they're separating them in this second dimension. And now you have things that would be co-eluting that you could completely resolve with the multiple spectra. So this is for things that are very similar. This is the probably the best technology that we have that's available for it. Here's a extreme example of what they're doing with high resolution separation. So in one-dimensional GC, you get that mess. Okay, there's hundreds and hundreds of peaks there. But now they run this. This is a fuel sample, and they run this in a different dimension. One of the things that led to the development of this technology is third world countries illegally selling crude oil to fund arms issues, to supply private armies, especially countries in Africa. So the government set out a proposal. They wanted to be able to identify every piece of crude oil and try to figure out what well this came from. And this was the technology that they can do that. So almost every well in the world, we've mapped out, and we can actually take the crude oil from that well, take a complex mixture like this, and we can figure out what hydrocarbons from that crude oil identify back. So we can at least track, can't eliminate black market crude oil, but we can track what's happening with it. I mean, the big thing, Iran's their crude oil, they're using it to fund their nuclear program. How can we track that? Just going back to the other one, GCMS, we've talked about this and looked at it a little bit in the lab. Standard GC column injected into the mass spec. Now the power is that you can take any component that elutes, and now you've got a mass spectra associated with that, and can give you high assurance that this is really the peak that you think it is. So GCMS is a really, really powerful tool. And when we do the advanced lab, we do a lot of our advanced analytical, we do a lot of things with the GC mass spec. Okay, so that's the end of 27. We're going to roll right into 28. Save that. And 28 is somewhat similar. It's got, we're going to go over some fundamentals and then talk about some applications at the end. Put over here. So, topic of 28 is HPLC. So, we're going to talk about the classification of HPLC, why it's necessary to use it, a little bit about the instrumentation, and I think I actually mixed these up a little bit. Pumps, injection, detection, and then talk a little bit about the different types of chromatography, and absolutely minimal about these last two, but we're going to talk about reverse phase and normal. Reverse phase is by far the most common mode of liquid chromatography in HPLC. A few problems to suggest you look at before the exam tomorrow. So when you take HPLC, now you're looking at the possibility of looking at non-volatiles, things that are thermally labile. So you can look at intact macromolecules like proteins and carbohydrates, large saccharides. Generically, we break it down into these classifications. If we do separation of large compounds, I'm going to start down the bottom left. So things above, let's say, a few thousand molar mass, up to as large as you want to go, that's size exclusion. We also call it gel permeation, and this is if it's organic soluble. If it's a water soluble, it's the same technique, but now we call it gel filtration. So same technique, you're just using to a different mobile phase. So your stationary phases have to be different when you go from an aqueous system to a non-aqueous system. Ion exchange works on large and small molecules, so it can work in both worlds. In the world of small molecules, so things less than a couple of thousand, normal phase or absorption is the most common. So you use a solvent like hexane, so a very nonpolar solvent. If your compound's soluble in methanol, you'll use something like reverse phase. You can do some small molecule gel permeation with solvents like THF, but it's only going to be good to separate compounds that vary at least by 20% in molar mass. So if you had trying to separate some polyaromatic hydrocarbon versus a chlorine substituted polyaromatic hydrocarbon, there's not a difference in molar mass that size exclusion is going to work. If it were a dimer or something or twice as large, then you could do it. But it's typically things that are larger. There's better ways to separate it. Then when you go to the water solubles typically we're either looking at reverse phase or some form of ion exchange chromatography. And we'll talk about each one of those just a little bit. So the 5 areas that we could break things into are partitioning, which we call reverse phase, absorption, which we call normal phase, ion exchange, size exclusion, and there's one that the textbook doesn't mention much called infinity. Infinity chromatography most commonly is based on the use of monoclonal antibodies that are specific for some antigen. They let you pull needles from the haystack. But today we're learning how to do molecular recognition solids that can work in a similar fashion. They're much, much easier to make than a monoclonal antibody. So you can develop those types of stationary phases as well. The major difference between traditional liquid chromatography, so like we do in a gravity flow column or TLC, and HPLC as a technique is just simply the particle size. If we're doing something like TLC or gravity flow column, our particles are somewhere from 100 microns to 250 microns, and it doesn't take much pressure to get the solvent to go across it. In HPLC, we decrease the size of the particles substantially because the particles are now close to one another. The pressure drop to push the solid or the analyte across the column is quite high. So the original name was high pressure liquid chromatography, and then it changed to high performance because the peaks got so sharp. But it takes a pump. It takes pressure to get things across. The big reason of why is down here at the bottom. LC can analyze non-volatile thermally labile compounds. And the reason that's so critically important is that 75% of the things in nature fall in that category. So all the compounds that we know, 75% of them are in the form of non-volatiles. So we need a way to analyze those. GC is not the answer for everything. What kind of market is there for this? It's huge. HPLC sales exceed $5 billion a year. There's one company called the Waters Corporation in 2014. They did $1.9 billion worth of sales, and they've got about 6,200 employees. They're one of 5 large HPLC companies. And that's not all they do, but that's the bulk of their sales. Why does HPLC so successful? Number one is the sensitivity. You can see things at much lower concentrations than you can with thin layer chromatography. The use of inline detectors allows you to more easily quantitate, because now instead of looking at a spot, you've got this peak on a chromatograph that you can quantify with. You now have the ability to look at that other component that GC can't see. You can look at non-volatiles, and the reproducibility of the technique is very good. I mean, it's hard to get 2 TLC plates to reproduce within 5%. HPLC, you can easily do 1% if conditions are set right. In HPLC, the saying is particle size rules. Now, we talked about Van Diener equation earlier in chapter 26, and we talked about we wanted to minimize our plate height. So a Van Diener equation, our plot, is a plot of plate height versus the flow rate, and we want to find this minimum, the low point. That's our sharpest peaks. So with 10 micron particles, the peaks may be so sharp, but if we cut the particle size in half, the plate height comes in half. And if we even start going smaller than that, what happens is the mass transfer gets so small that this almost flattens out. So what this means is I can run faster and faster and faster and not have a bad influence on efficiency. So if I can, instead of being stuck at this flow rate, which is maybe 3/4 of a mil a minute, if I can get a good separation in 5 mils a minute, I'm going to get the separation 5 times faster. So times money is what it comes down to. And this is the same things illustrated in this next plot on the other side. This is showing where the future is going into these particles that are less than 2 microns. So when you get less than 2 microns, this really, really flattens out and allows you to run higher and higher flow rates before or without any increase from the mass transfer effect that's causing the decrease in efficiency on all these larger size particles. So the trend is now 3 microns and less. There's a technique called UHPLC, and it is particles that are less than 2 microns. So UHPLC, ultra high performance, less than 2 micron particles. And it requires very high pressure to accomplish that. To give you an idea of what you can do with UHPLC and why it's gaining popularity, these are 2 separations that are achieved with HPLC and UHPLC. Standard HPLC, the separation is done in 30 minutes. UHPLC, the separation is done in 4 minutes. The other thing you look at is the amount of sample that's consumed. With the standard separation, you injected 20 microliters on the column. This one, you injected 1 microliter in HPLC. How much solvent did I consume? Because this was running longer, it's pumping in a mil a minute, I used 30 mils of solvent. This one, I only used 5 mils of solvent. So this is the future. I'd love to have one of these. I tried to get one a couple of years ago, but it's $70,000 to open the door to get one. They're still, right now, until the market fully meets the demand and drives the cost down, we're just going to buy some extra solvent and take a little longer to run our experiments. There's some advantages to it, but it's just, it's pretty expensive technique right now. All right, I'm going to come back to this towards the end of the chapter, but I just wanted to let you start seeing this visualization of what's happening with the different modes of chromatography. I taught a short course for was Hewlett-Packard at the time on HPLC in Frederick, Maryland, about 20 years ago when I was right out of graduate school, 25 years ago, 30 years ago, whenever it was. And one of the things that I talked about were the mechanisms of HPLC and the way that the techniques varied from one another. So in normal phase or absorption chromatography, you actually have a physical absorption on the surface of the solid mobile phase. In reverse phase, it's a liquid-liquid partitioning event. So you have a liquid and a liquid, and the two things interact with each other. So you've got a mobilized liquid, so a liquid stationary phase, and you've got a liquid mobile phase, and the analyte has a partitioning event between those two phases. All right, in ion exchange chromatography, what's happening is you have electrostatic interactions and opposites attract. So if you want to separate out cations, you put in an anionic stationary phase, and based on the extent of that electrostatic interaction, you can separate different things out. And then size exclusion is based on the concept of molecular entrapment. Small molecules can migrate into pores of a stationary phase where large molecules are going to be blocked and can't do that. The large molecules elute off the column first. Small molecules elute some period later, depending on how much they're entangled or they're entrapped in the column. So in HPLC, we have stationary phases that are packed inside of columns, and they have some type of a coating on them for the most part. And typically, the particle sizes are going to be a lot smaller than what we used in GC. Now, packed columns are not that common in GC, but even when we do, we use pretty big particles. Here we're using small particles. Most common type of particle uses some type of a silica particle. Most common shape is spherical because we can pack that more uniformly. And the idea is that you want all the particles to be exactly the same size, or monodispersed is the term for it. And typically we're looking at things that are going to be in the neighborhood of a couple of microns to 10 microns. And the idea is to get the particles packed together so tightly that the dimensions between all the particles are very similar. So that minimizes that A term of van der Waals equation where you have different paths that particles can take. So if everything's got the same choices, is the minimal variation there. So what's different about these particles is that most of the particles have a secondary type of porosity in that they're kind of like a sponge. So they have channels inside of them that allow the analyte to diffuse inside of the particle and allows for enhanced surface area. So I kind of showed you this picture a few days ago, but I'm going to go back to it and add some things to it. Here are examples of two different types of particles. The one on the left is 70% porous, and it has a surface area of 300 square meters per gram. All right. The second one has a porosity of 50%, and it has a surface area of 150 square meters per gram. So if you were kind of do a cutaway of that, this is kind of like it's an anthill. All right. That's the thing I think about when I think about this, is that it's just tunnels going through this thing everywhere. And if you look at like this one, only 30% of it is going to be the black. It would be 70% white or open. And everywhere where there's a surface, there's a place where you can put this bonded mobile phase on it. You can actually get a large amount of carbon per gram of this material on the surface. So that's one of the ways that we compare the surfaces, how much carbon's there. Just briefly threw this slide up about some of the different types of chemistries that can occur. If it's a silica particle, it has SiOHs on the surface. And there's a couple of different ways that we can bond these. One way is we take and react it with a chlorosilane compound, and we can add our C18 group to it like that. It's going to give off HCl. But that's still, you've got a fragile bond here that can break pretty easily. So to give more stability, what we'll try to do is react it with a trichlorosilane and trying to get one or two or three groups to bond with a surface to try to maximize the stability of that particular compound. I mean, ideally, I like to get all three of these things bound, but it's geometrically hard to accomplish that. And then where there's any leftover groups, we can come and end cap those with a short end capping, something that can penetrate into the surface. So like this group at the bottom, any silanols that are left, we could react with chlorotrimethylsilane, and that would end cap to get rid of all of these SiOHs. We want to eliminate the possibility of SiOHs. That messes up our chromatography. So there's a new technology that's came out in the last 4 or 5 years. They're called core shell particles, and they really have a lot of popularity with the UHPLC. And the idea with these is that they take a complete solid support, so something that's non-porous, and on top of that, think of it as a glass marble, they coat a spongy-like material on the outside of it. So what happens if it's completely spongy under pressures of 20, 30, 50, 60,000 psi, it collapses and shrinks down. But this gives it some rigidity to the core of the particle that keeps the particle from collapsing on itself. So now you've got something that's got a pressure limit of up to 1,000 bar. So that's usually we run a column that's about a 5,000 psi limit, and that's a pump limit of about 5,000 psi. 3,000 about an upper limit on the particle, but now you got something that'll run 15,000 psi. So it's a lot stronger, more stable particle. Those give us a lot of capabilities to go faster, and you can go faster and faster and faster. These things that are less than 2 microns, that's the driving force. There's a core underneath it that's a 1.25 micron, and then it's got a shell on the outside that's 0.23 on each side. These are really, really strong and powerful support particles. So of the stationary phases, the most common is when we take and use a nonpolar stationary phase combined with reverse phase chromatography. And then the mobile phase is going to be some hydroorganic. So it's going to be water mixed with something else to make it increase the strength. We'll talk about the something else, but typically the most common one is the octadecyl, the one that we use, the C18 group. To have a little bit less retention, you can use an octyl or C8 group. And if you want something that's slightly different, that's got some different polarizability, you can use a phenyl group on the surface. The more strongly the analyte interacts with the stationary phase, the more it's going to adhere. So what happens is that retention relates directly to the amount of that interaction. If we want something that's less polar, or less nonpolar, and has more polarity to it, so we can capitalize on those type of characteristics in a molecule, we can use things like an amino group, a cyano group, or a diol group. Same way we do in GC. There are a lot of different options where we do different types of stationary phases. So if we look at an HPLC system, in terms of a schematic view, there are a lot of similarities between the different systems. There is a generic separation between the two types, and those are ones that are isocratic, which means it's capable of delivering a single mobile phase all at the same time. You never change it. Or one that's capable of running a solvent gradient, so it changes the mobile phase composition as a function of time. So now you're going to take a mixture of different components from 2 or more solvents and mix it together. A good system will let you mix 4 different solvents, and you somehow regulate those so that they come into this valve. They're coming down here to this valve that mixes them at the proper proportion, and from that, they're mixed at low pressure, and they go into the pump, which creates the pressure. They do something to make sure they're mixed well. There's a series of regulators that are monitoring the pressure. There's a pressure transducer in here, the place where the sample is injected, and then there's the separation or column, and finally a detector at the end of that. Now there are 2 primary ways that the columns work, or the pumps work. There is one that do low pressure mixing, with 1 pump, and that's what this example shows. So there's this proportioning valve that brings as many different solvents as you have valves for, puts them together, and it lets how much of each one to mix. So at this point in time, you were 20% of this solvent and 80% of the other solvent. This valve electronically meters the proper amounts in there. And then you've got 1 pump that pressurizes these solvents. The problem is there's a delay in this mixing, because even if you're trying to make changes, there's some dead time that takes this liquid to flow through here. It doesn't instantly change and appear at the column. So a more high performance option, or say the Cadillac model, or the Lincoln Continental, depending on what your preference is, the BMW version, is high pressure mixing. So what high pressure mixing does is it uses multiple pumps and it controls the flow rate of each pump independently. So our system is 2 pumps. So it's got a pump that's pulling in solvent A, and it has a second pump that's pulling in solvent B. And if I want it to be 80%, I tell this one to pump 0.8 mils a minute. And if I want this one to be 20%, this pump's going 0.2 mils a minute, or any other ratio that I want to combine them. But both pumps are simultaneously going at the same time. Okay, the better system is the multi-pump system. How do the pumps work? That was kind of the technology that Horvat worked out. I told you all about Csaba Horvat, who's the guy that came up with HPLC earlier with the chromatography chapter. The thing that he had to come up with is a pump design that would operate at 5,000 psi. You want it to be pulse-free. You want it to deliver very accurate flow rates. And the reproducibility of this needs to be at least a 0.5% level. So the common design that's been adapted has a combination of a syringe that goes back and forth. And what happens is this syringe, it's got tight seals around it. Most commonly, these are made out of a sapphire rod that as it pulls back, it's just like a syringe as you would suck something up in the syringe. As the vacuum's pulled on this, and then there's a series of ball check valves, and one is the inlet side and the other one is the outlet side. Now, to show how these valves work, I've got another set of pictures. So what happens when the syringe goes back is this valve gets sucked down and it fits into the cup and it closes off. So it blocks the backflow coming back into the cylinder. So that means just the fresh solvent goes into the syringe. Then as the piston goes in the forward direction, the balls, as this comes out, this one goes down to the bottom. It seals off and blocks the flow from coming out. The pressure now goes onto the column. And it's continuously going forwards till it reaches an end, and then it will quickly retract and then go forwards again. That foam sound that you heard in the background with the pump going on and off. It's every time it does it, it makes a sound when it retracts. This thing's trying to maintain a pressure of a couple of thousand psi when it's doing it. So one of the things that's in these pumps is typically, written on top of it here, but this thing called a pulse dampener. And what the pulse dampener is typically a liquid area where there's a little bit, the middle has some elasticity, and the idea would be like putting this inside of a balloon so the balloon could expand and absorb the pressure pulse, yet the outlet would be the similar pressure as we could keep it. So pulse dampeners are standard on instruments as well. In terms of the injectors, the fixed loop injector is the most common type. And the company that, this little symbol's for a company called Rheodyne. I showed you all the injector looks like this. So what it is you have the loop. If you turn it all the way to one side, you're in load position. So you would take your syringe, and in this case, you put your needle right in the center. So it goes in the center, you push a sample in, and when the valve's in this position, it goes through and fills this loop up. And any additional goes to waste. So you actually have a loop here. So like on this one, I can read the fine print. That's a 20 micron loop that's there. So this piece of tubing holds exactly 20 microns. If I want a 2 micron loop, I use a smaller ID or a combination of ID and length that holds that volume. This is the load position. And then when I move it to inject position, what happens is I rotate the valve around physically. So it aligns, changes the alignment of these 6 different ports. Now what happens is the solvent that's coming into the system goes through the column, or goes through the loop, goes around, pushes out, and that goes directly onto the column. So the flow is now continuously running over the sample loop. And if I injected more sample, it would just go over to the waste. So as long as I filled this loop up, it's going to inject the exact same amount every time. Now I can do a partial fill of that loop. So if I wanted to only put in 5 microliters in this loop, I could, when I injected this, only partially fill it and do a partial fill. So I can do a partial injection, that's fine. So a partial filled loop is okay. But if I want the good reproducibility, I'm going to fill it all the way up. Now, if you do robotics with it, the robotics actually use a fixed volume loop, but they partially fill it because the reproducibility of the robot on the needle doesn't require that it doesn't have the problems that humans have when you're controlling syringes. All right, what do we use for detectors? Well, about anything that we've talked about this semester can be adapted to HPLC. If you can dream it, you can hook it up to an HPLC system. So the detectors can either be based on the bulk properties of the mobile phases and changes that occur there, or they can look at specific properties of the analyte. And we're going to look at a couple examples of both of those. So the most common is the one that we use. That's the absorbance. So in the UV vis, the requirement, though, is that your compound has to have some type of chromophore. It has to absorb something. So a downside is that this tube that's running across here, this tube that's coming in, is typically only a couple of maybe 10 to 20 thousandths of an inch ID. So there's not much of a path length across it. So the way that you try to get a larger path length, if you remember the equation for Beer's law, is that absorbance is equal to molar absorptivity times path length times the concentration. So to try to maximize the absorbance that we see, we try to maximize the path length. So we use something called a Z-cell. So our liquid comes in, and then we make it go through a right angle and put optical windows on each end, and we shoot the UV radiation, our visible, along the axis of the column. So now we can get things that have path lengths that are going to be a couple of millimeters all the way up to a full centimeter. And we can do this in something that has a volume of only a few microliters. Now you can get cheap ones that cost a couple of $1,000s that are filter based. So if you want to do protein work, commonly on proteins, you go after 254 nanometers or 280. You can get a UV lamp, isolate that with an interference filter, and you can get a detector for a few $1,000s. More commonly, they're going to be monochromator based, and depending on the quality of the monochromator, you're talking about a detector that's maybe $5,000 to $6,000 to a diode array system that's going to be $15,000 or more. The advantage of diode array systems is that now you can get real-time spectra of compounds as they elute off the column, and I showed you an example of this in the lab. Here's a similar example. This is a mixture of steroid compounds that are eluting, and on this example, and this is old data, I mean, here it's taken a spectra every 5 seconds. Monitor systems like ours can do up to 25 spectra a second, so 25 hertz. So that would be 125 times faster than this application. And this is a brand new textbook that came out that you're using some old data. But it shows the spectra in this dimension versus the absorbance versus the time in this dimension. So you can see the different things that have different maximas as they elute off the column, and each one of these represents one of these different steroid type compounds. So we can use it to confirm the identity by looking at spectra. Fluorescence gives us the great sensitivity, just like we do in a traditional fluorescent system. We observe at a 90-degree angle from the excitation. Typically, you're talking about a 3 to 5-fold enhancement in sensitivity over absorbance. The problem is, same way with fluorescence before, only 3% of compounds in nature fluoresce. What we do now is we use derivatizations, and we can take advantage by adding a fluorophore to a particular functional group. Like if it's reducing sugars, we go after the ketone or the aldose group. If it's an amino acid, we can either go after the N-terminal or go after the C-terminal. Any type of functional group, we can devise the chemistry to come up with that. Now, something that's more bulk property based is a detector called refractive index. And this is not as popular as it used to be, but this is one of the old detectors that we had. I've still got one sitting up in the lab in there. But what it does is it bends the light as it refracts at a different angle as the analyte goes through a series of windows. I'm going to show you what I'm talking about here. So you've got a light source that's producing some light, and that light goes through a cell that's at different angles, and as you've got a reference solvent you have to put in there. It doesn't have to be pumping constantly, but some representation of the mobile phase, and you've got your sample, which is primarily mobile phase. But if you get to the point where the sample starts to influence the refractive index, it's going to cause, when the sample comes through, the light to refract at a slightly different angle. Okay, remember Snell's law we talked about earlier in the chapter? And as it bends the light away from the detector, less light's going to hit the detector because this light beam is going to be distracted up here somewhere. So the good thing about this is that now you don't have to have a chromophore. You can see about anything. They're fairly reliable. It's a universal detector. The problem with it is that it's pretty low sensitivity. The other thing that makes it a little bit more complex is that when the peaks come off of it, depending on what the refractive index is, sometimes it results in positive peaks, sometimes it results in negative peaks. It just depends on what the refractive index is of that particular compound. Now, we can deal with negative peaks. That's not a problem. We just have to know what we're looking for. So that's a possibility in systems. Another bulk property detector, which has largely replaced refractive index, is called an evaporative light scattering detector. And this is a newer technology. It's introduced in around year 2000. And what it does is it takes a sample and volatilizes the solvent out, and then it produces the non-volatile species that will make a colloid and group together. And this works very good for things that don't have a chromophore. And a good example of this is a great carbohydrate detector. So what will happen is that in the nebulization process, and this is a heated gas of nitrogen, the mobile phase evaporates out, and you form these sample droplets, which are a colloid particle. And as those come down and strike a beam of light, part of that light gets scattered to a detector, and you use a high-intensity beam from a laser. And the more particles you have, the more the light gets scattered towards the detector, so it's direct proportional. Now, some things are more prone to form colloids than others, and there are some things that you can do to try to encourage that by putting things in there that, like a little bit of silver chloride or something that's got a low solubility that would initiate a crystal or colloid forming. But it's a good option for things like carbohydrates. Electrochemical. In the industry, I use electrochemical detectors a lot because as long as you've got something that can interact in a redox reaction, you can measure that. Anything that's got an amine or an alcohol or an aldehyde or about any group, you can electrochemically measure that if you understand something about the chemistry of it. Conductivity is another thing. If you're doing ions and you have a non-conductive solvent, you can just look at the gross conductivity of when that ion passes in front of a cell. Mass spectrometry, it was a difficult thing 25 years ago. Now it's a household technique in labs because of the advances with electrospray ionization and atmospheric pressure chemical ionization. But now you've got a detector that starts at $100,000 and goes up to millions. So it's not a cheap option in systems. It's an expensive option. So table 28.1 does a comparison of some of the common types of detectors that we use. And these are things that are, for the most part, all commercially available, with the only exception is optical activity. And if you look at the sensitivity on them, most of them are picogram range. A few things can see down in the femtogram. In fact, fluorescence, if you combine laser-induced fluorescence, if you go femto is 10 to the minus 12th, then we go start using our femto is 10 to the minus 15th grams. The next term is atto, 10 to the minus 18th. And then the term you've probably never even heard of, a yocto. A yocto is 10 to the minus 21. So now we're talking about if you got a yoctomole of something, you got 100 molecules or 100 atoms of these things. But with laser-induced fluorescence, that's absolutely doable. So we can actually do single molecule detection today with laser-induced fluorescence. That's ultimate sensitivity. Mass spectrometry, again, is one of our powerhouses. It's good for less than picogram. FTIR is not as sensitive. Some of these things are only good down to microgram. But if you're looking at something like how much sugar is in a Coke, you've got grams of material to mess with. So sometimes you don't have to worry about sensitivity issues. You just need a sensitive or a method that can see your analyte. A lot of options that we have for detectors. Okay, so one of the things that's important to understand is the difference between reverse phase versus normal phase, and how to be able to predict how the analytes would migrate down the column in terms of their elution order. So on this example, we've got a group of compounds whose polarity A is the highest and C is the least polar, or the most nonpolar. So what happens with reverse phase is it uses polar mobile phases, and it has a nonpolar stationary phase. So with a nonpolar stationary phase. What happens with normal phase is it uses a nonpolar mobile phase with a polar stationary phase. All right, so like attracts like. So what happens with normal phase chromatography is the compound that is the most nonpolar, C, elutes first. And the thing that is the most polar interacts with that polar stationary phase the most, so it elutes last. So as I start with something that's a highly nonpolar solvent, like hexane, I get high retention. And if I want to get a stronger solvent, I can add something like a few percent methanol to that, and now that's going to drive everything off the column quicker. It's still the same retention order, they just elute quicker. All right, in reverse phase, now things have switched around. Now I've got a nonpolar stationary phase, so the most nonpolar column, or component, is the thing that sticks the most. The most polar compound comes off first. So the most polar compound was A, so the retention order is going to be ABC, and the key thing is that the two things are completely opposite of one another. CBA versus ABC. And I start with something that's a highly polar mobile phase. So in a hydroorganic solvent, it's going to be low percentage of organic, mainly water. To increase the strength of the solvent, I increase the percentage of the organic in the mobile phase. So we started with 5% acetonitrile water, and then we ramped it up to 55% acetonitrile water in our separation that we did with caffeine. Okay, so if you'll look at the old test questions, a lot of times I ask you something about retention order with normal phase versus reverse phase. So what do we make the mobile phases out of? Well, in GC, what we controlled was temperature. That doesn't work as well as in HPLC. So in LC, what we do, the variable that we alter is the mobile phase composition. And we change the polarity of the solute or the solvent that's being pushed down the column. It's a little harder to do, certainly, than changing the temperature in an oven is trivial. Changing the composition of solvents on the fly is a lot trickier thing to do. So if we think about in GC, if there's only two polarities involved, that of the analyte and that of the stationary phase, it's a simplified partitioning event. But in LC, we add a third dimension, because not only do we have the stationary phase and the analyte, now we have the mobile phase. But this is the one that we can most easily vary to change the nature of the separation. So one column can do a lot of things in HPLC. So the rule of thumb that we use for choosing our solvent is we have to look at what are the intermolecular forces that are going to exist in that compound. So what are the functional groups that are going to contribute to its polarity? And if we think about polarity in terms of the things you learn from organic and your other classes, hydrocarbons are the least polar, then ethers, then esters, then ketones, then aldehydes, then amides, then amines, then alcohols. So we look at those in terms of that order, and then we look at how many of those groups are there. And from that, we should be able to make an educated guess in terms of retention order. For reverse phase, or partitioning chromatography, it's best to use the stationary phase, a polarity of opposite of the analytes, and dilute with a mobile phase of a different polarity. All right, so we typically use a less polar bonded organic stationary phase. That way we can use a more polar mobile phase to elute the compounds off the column. We don't want the interaction to be too strong, or we have to waste a lot of organic to get things to come down the column. The most common mobile phases that we use for reverse phase are going to be aqueous-based systems that are combinations of water with acetonitrile, arm-methanol. A third one that I didn't put on here is THF, tetrahydrofuran. Tetrahydrofuran has a negative associated with it, is that it can form epoxides over time, and those epoxides can be explosive. So you don't want to pick up a bottle of THF that's been sitting on the shelf for 30 years. That can, especially if it had a metal cap, it can be a bad situation. So it's not used as much, but in industrial settings, it's got some use. But we mix different ratios of those solvents to change the strength of the mobile phase to get things to elute off of our column. So again, those are our three solvents that we use. Those are the most common one, but if we go to normal phase, the number of solvents that we can utilize is greatly expanded. And one of the things that we talked about in analytical when we did our thin layer chromatography experiment is that the difficult thing is knowing what mobile phase to use to get the separation in TLC. It's easy to spot a plate and drop it in a beaker and develop it, but what do you use as a solvent? And this is just a partial list of some of the different compounds that you can use as solvents. So things like hexane are common solvents. If you want something that's a little more polar, you can use an ether. You can use diethyl ether versus propyl ether. You can use chloroform. Ethyl acetate's a common solvent. Methanol. If you really want something that's a high polarity, you can add a small amount of water into it, but that's such a strong solvent, it typically doesn't work well. It changes the viscosity of the solutions to the point. We compare the strength of solvents in normal phase chromatography with something called the allotropic series, and that represents solvent strength. So this is a table I stole from a different text just to highlight these ones. This is also a portion of this table that's in the book. But just to look at the common ones, things like cyclohexane is one of the absolute weakest solvents that we can have. So it's got a value of a negative 0.2. The reference is actually octane in this system. It's assigned the value of 0. But hexane is 0.01. And then when you start looking at slightly more polar compounds, something like ethanol is 0.88. Acetonitrile is 0.65. Ethylene glycol is a little over 1, but water has a value of affinity. It's much more polar than a silica stationary phase. But we blend solvents to get different separations by putting them together. So the way that we overcome the elution problem in HPLC is we change the composition of the mobile phase as a function of time. That's called a gradient. In GC, it was a temperature gradient. Now it's a mobile phase gradient. You start with the weakest solvent. So in this case, it's 30% acetonitrile, and the strength of that is increased over the separation, or the course of the separation. And this was actually a publication the authors used from our textbook last semester, from the chemical analysis textbook by Harris. And the authors, like this publication, they've been using this separation, they've been using it for a number of years. They've been using it 15 plus years. But me looking at this, all I see is this wasted time. So if I would have taken this separation to my boss and said, hey, I got this great separation in 40 minutes to separate these 8 compounds out, give me a high five. He'd say, go back to the lab, get it done in 10. Because that's using a huge amount of solvent, and you got all this dead time that's in here. If I were to design that separation, I'm going to do it in a way that you've got a couple of closely eluting compounds. So yeah, let's go here. But now to get this off, I'm going to do a very, very rapid jump to get to there, then probably a slower ramp up here to 80%. Make sure we can resolve those, but I'm easily done within 20 minutes, if not 13 or 14. It's a good separation, but when you look at something, this is a resolution greater than 10 between this pair, between 7 and 8. Why? I mean, that's just, if you look at this one, this is probably a resolution of close to 20. I mean, that's wasted time is all it is. You need a solvent system that can get those things off faster.
Is that something like your first one you run, you see that, and then
Yeah.
adjust as you go?
Yeah, it's a process we call method development, and you start with a generic gradient. I mean, that's a 2-step gradient. Usually, most of the things that I do are a single step. So you'll let it run with just the starting conditions, and you slowly ramp it up. And the same way on a GC run, you learn from what you see, and then are your peaks too close together, they're too far apart, you make adjustments to get optimized conditions. So a lot of that comes with experience and just playing with things and learning how things are going to respond with this example, mobile phase composition, and GC, it would be oven temperature. But it's you learn to get the most optimized conditions. In an industry, the big thing is time is money. I mean, if I've got 5,000 samples to run, and if I can run them in 10 days versus in 50 days, I've saved the company a lot of money. So those are types of things that you have to look at. I mean, you always have the option of, if I had 5,000 samples to run, I could go to my boss and say, hey, and I need these $80,000 HPLCs. I need 10 more of them in a month to run all these samples. Or, but if you could increase the throughput of your instrument by a factor of 5, now you could maybe do it with 2 more instruments. So those are, and when you look at things like, we did a lot of development for things that would go out into the field labs. So like at each plant had its own quality control lab. And we would have to develop the technique that would give them as quick an answer as possible and be the most reliable. So those were all things you have to consider. Here's an example of changing the stationary phase a little bit and how that changes the separation. So this is a methyl group. It's the stationary phase. And you've got these are just a group of compounds that are used as model compounds, but you go something like uracil is highly water soluble. It usually represents, is added in reverse phase to represent the T0 peak, the void. Right? So if you didn't have that in there, there would be a baseline disturbance, but this is a strong UV absorber. So you put it in there to clearly understand where T0 is. And then phenol is pretty polar, and then you start going to compounds that have more and more polarity. But the methyl group, these elute in about 8 minutes. This last one, toluene comes off. If you change it to an octyl group, put a C8 on there, now instead of 8 minutes, it's almost doubled. It's at 15 or 16 minutes. And if you put the C18 group, the octadecyl, now you're eluting this guy off in 20 minutes plus. Wonderful separation, but is this good enough? Or is this good enough for you? You've got to decide what's good enough for that particular separation. This is an example of 6 different steroids, and this is a figure out of the textbook. And these are all separated with isocratic, so they're not changing the composition as a function of time. But it gives a good example of how difficult it can be. So here the first thing that we had was 41% acetonitrile, 59% water, 1, 2, and 3 cololute, and they can resolve 4, but 5 and 6 cololute. That's not good. So they did a 70-30 mix, and now 1 and 3 cololute, 2 is almost coeluting, 4 is isolated, 5 and 6 are close to one another. Then they changed to methanol as a solvent and did 49% methanol, 51% water. The same mix as organic to water as the one above, but now methanol is a weaker solvent. So even though it's 49%, where urethane's diluted in 2 minutes, now the last compound comes off in 7 minutes. And you've got a little better separation. So peaks 1 and 2 are resolved a little bit. 3 is isolated. 4, 5, and 6 are in good shape. So they changed now to THF. And in THF, they got 1, 2, 3 separate good, 5 separate good, but now 4 and 6 colute. And the separation that they think is the best is a 3-component mixture: 11% acetonitrile, 12% THF, 77% water, and it's not resolution greater than 2.5 where I'd like to be, but at least their resolution's greater than 1.5, and all the components are fairly well resolved in a 7-minute run. Now, that seems great, but I could easily separate that in 5 minutes with a gradient. So, however, a lot of times, like in quality control labs, they prefer to have an isocratic system because now you don't have to worry about somebody that's not experienced with HPLC putting the wrong solvent in the wrong bottle. If you know solvent goes in the instrument and it's the solvent, there's not multiple solvents, you choose the simplest system. Now here's an example of a much more complex separation. This is an amino acid analyzer. So this separates out 30 amino acids. Some of them are common amino acids. It does the common 20 and some of the non-common amino acids like methylhistidine and some derivatives there. The aminodipic acid. But the gradient that's on this one is a much more complex shape. It's a curved shape to resolve those compounds, and then it has a linear gradient at the end. So this separation's taking 47 minutes in time. That's a decently long run. This is a 25 centimeter column, but for almost 50 years, this was as good as we could do in terms of amino acid separations. So almost all of the work that we did since the first amino acid analyzer was introduced that used a similar technology to this, it took a 2-hour run. So this separation was developed in the mid-80s. It took an hour, basically, because you still had to regenerate your column at the end, get it back to the initial conditions. You were investing about an hour in every run to find out what amino acid this was in a sequencing event. That's a technology that we were able to overcome using other techniques. Right, just some advantages and disadvantages of the different size columns. If we look at high-speed analysis, so one idea or one concept that's been embraced is to do things quicker. So you can do short analysis times with short columns, and you've got an easy conversion from going from a traditional analytical column to these fast columns. The disadvantage to it is that your instruments have to have very low, what we call void volume. You can't have dead space anywhere. Otherwise, that dead space creates band broadening you can't deal with. And also, your detector system has to work very fast. So just giving examples of traditional columns or something like a column that's 20 or 25 centimeters in length, and then the fast columns are columns that the length is substantially reduced. And then typically that's combined with smaller particle size. So this example is a 6 centimeter column. And the difference in the separation, it allows you to do less packing material in here, so you can run a higher flow rate. So you're running 5 mils a minute flow rate, and you're getting the separation achieved here in 1 minute versus 9 minutes on the traditional column. The downside to it is you're eating a lot of solvent. But total solvent that you eat is about the same to get the compound off the column. You're just doing it at a higher rate, but still it's using about 10 mils in this one and about 10 mils of solvent in this one. Quicker is better, right? The next example I've got is looking at changing the diameters of the column. So the big push today is to go to the smaller ID columns and to go to the smaller particle sizes. So this is an example of a conventional column that's 4.6 microns internal diameter versus one that's 1 millimeter internal diameter. So 4.6 millimeters, sorry, versus 1 millimeter. So at a flow rate of 1 mil a minute on a traditional column, you get the 9-minute separation. With the micro bore column, it's a 1 millimeter. Now I've cut the flow rate by a factor of 10. I get almost the same time. So now I'm using 1/10 amount of solvent. And the other thing, what's the other thing if you compare these two, what's something that pops out at you? Sharper peaks. So the same concentration is going to be taller, easier to detect. So the sharper the peaks, the better the sensitivity. So this gives an example of different size on some examples or separation of polyaromatic hydrocarbons. This is a traditional column at 4.6 using a mil a minute, and they go to a 2 mil ID versus a 1 mil. These are the same concentration of every sample. But look at the peak, how big it is here versus how big it is here. If I want good sensitivity, I'm going to the top one. Okay? Our instrument can run this pretty well. So our HPLC can run this flow rate at 200 microliters a minute. Ours can't maintain the 50 microliter per minute flow rate. That takes a specialty pump. And we haven't got that yet. So when one of y'all became a doctor, y'all can donate $100,000 to the university and in lieu of buying your first Ferrari, and we'll get some newer technology. Okay, so if we go back and just think about those mechanisms now, the normal phase is the absorption. So you've got a polar particle here. So this is silica, if we think about it. Silica, SiOH, is on the surface. And you have absorption based on the interactions between hydrogen bonding or dipole moments that are formed with your particle. In reverse phase, you've got this liquid that's bonded to a surface, and you have a liquid-liquid partitioning. The other two I just want to say a little bit about are the ones at the end, the ion exchange. That's just a separation of some. This is just showing the separation of things with different strength of solvents. I'll talk about it just quickly. So this is 90% acetonitrile. Everything elutes with a void in 2.5 minutes. 70% everything co-elutes 2.5 minutes with a void. Drop it down to 50%. Here's the void time, 2.5 minutes. I'm starting to get some retention of the analytes. And keep working down to 30%. Here's my void time. All my compounds are well resolved, but now I'm 35 minutes invested in the column, in the separation. So on this one, what would be best? This is not pure. That's a shoulder on here. So it needs to do something to try to resolve those, but all these other ones, I can do something to try to get those peaks closer together. Otherwise, you've got too much dead time. All right, here's the ion exchange stuff I thought was the next slide. So your stationary phases are going to be resonance of either cations or anions, and you're using the opposites attract. So your mobile phases are going to be something that's aqueous, and then it's going to be a counterion that's competing for that stationary phase. So like on this first example, I'm separating out anions. So your stationary phase is going to be something like a quaternary amine that's going to be adhered to the surface, a positive charge. And for competition, I would want something that's going to be in the background that's going to compete with that ion. So my stationary phase is going to have something like the sulfate in it. So as these different analyte molecules come along and are competing for that positive charge, it's got something to compete with it. Okay, so you usually start with the weakest solvent, it's just going to be water, and you increase the ionic strength of the solvent to get more elution off the column. So they're mixtures of water and some salt. So in this example, it's a separation of anions. Now, why the different things, all these things that are a -1, for example, why do you think they would separate on the column?
They can have like stronger dipoles, or they can be like more strongly negative.
Well, they're still -1, but you're on the right track in what you're saying. The terminology we use to describe is called the surface charge density. So if you look at a small ion versus a large ion, right? That -1 charge is spread over a small area versus a large area. So the surface charge density decreases with the size of the ion. So you can easily separate things that have the same charge based on different surface charge densities. And you can do the same things with cations. So this is an example of a separation of cations. Again, all these +2 cations are easily separated because the ions have different sizes, therefore they're going to interact with a negatively charged stationary phase differently.
So basically, the bigger it is, the more interaction.
Actually, the bigger, the less interaction it has.
Why is like the fluorine a loop first?
Okay. Okay, so if you look at fluorine, and that's the, let me show you where to, I think we're in the notes. I'm going to go back and I want to show you this. That's a great question. But this is the best way I know to answer this. So back in analytical, way back when, we talked about ionic strength. Let me see this chapter. Yeah, it's got to be the next one here. All right, so what happens is the hydrated radius is what controls these things. So if you look at fluorine, even though fluorine's the smallest ion, it binds water molecules to it so tightly, it's got the largest hydrated radius. So bromine's huge in size compared to fluorine. So bromine weighs 80, fluorine weighs 20, so at least 5 times or 4 times bigger in mass, but water molecules bind to the bromine molecule less, fluorine being the small one. That's the reason it elutes off first. So it's not the physical size of the ion, it's the hydrated radius of the ion that plays the role. So that's the best way I know how to show you these. But things like the nitrate and the chlorate and the sulfate, all these things are going to be, the smaller it is of its hydrated radius, then the more tightly it binds to the column. The larger the hydrated radius, the least down the column is. Okay, all right, so just a couple of slides somewhere through. So the last couple of things are just some examples of different types of separations, and these shouldn't be on the same slide. These are 2 different topics, and I just want to isolate those things. So just talking about size exclusion chromatography, you're talking about typically polystyrene stationary phases versus a silica gel. And if you're doing an aqueous-based system, it's called gel filtration. If you're doing an organic-based system, it's called gel permeation. So a common stationary phase that you use for aqueous-based separations is a gel compound called Suffidex. The gel uses Suffidex separation biochemistry in a column to separate some, typically use it to separate some like dimer large proteins for small proteins or dyes. Its main use is in biological applications. But again, you have to have large differences in molar mass to be effective in size exclusion separation. This is just the figure here is a separation of amino acids that's similar to the one that's shown on the previous, but this one's even more complex in terms of the different amino acids that are in this mixture. So how do we look at things like carbohydrates? So carbohydrates are among the most complex things to try to isolate or separate because they're all combinations of CHO, and they have very similar polarities associated with them. So this is a column that's designed to bind particularly carbohydrates, and it looks at the way calcium binds to carbohydrates. And the way that metal interacts allows you to resolve all these different sugars and to separate them out. The detector that they're using here is a refractive index detector. The solvent, mobile phase, pure water. Throw some water in there. So this is a very polar type column that's got calcium bound to it, and you have dipole-dipole interactions between that polar stationary phase and the polar molecules. All right. So you look at something like polyaromatic hydrocarbons in water. Problem with PHAs, even though they're straight hydrocarbons, combinations of carbon and hydrogen, the aromatic ring nature of them makes them non-volatile. So if you heat them up, they won't go across the GC column, they'll decompose. The EPA has identified what they call the deadly 16. All right, and that's this group of polyaromatic hydrocarbons that are found in a variety of different industrial processes. And these things can get in the environment. The bad thing about polyaromatic hydrocarbons, because of their nature, excuse me, they're planar systems. And the things that have, the things that Wasman didn't see, that the things that have planar shapes associated with them will bind in your DNA very well. So these bioaccumulate in fat cells, in fatty tissue, and then they can interact with your DNA and cause mutations in DNA. So we're very concerned about the levels of PHAs in the environment. And these are things that, even though this separation is used in a reverse phase separation, this is actually using a column that's specifically designed for polyaromatic hydrocarbons. It has a aromatic system bound to a column. This is one of the first ways that we could look at all 16 of those in one run. Okay, here's the last thing I'm going to show you. So here's kind of where this technology has went to or developed. This is some analysis of work done by Richard Smith at Pacific Northwest Labs. And he introduced he didn't introduce it, but he became one of the ones to capitalize on it, is a method called top-down proteomics. And with top-down proteomics, traditional proteomics, what you do is you isolate a protein, and then you take and digest that protein in something like a tryptic digest to give you a mixture of peptides. But you have to get this protein from a 2D gel where you're isolating these different spots out, and you isolate that one protein and then digest it, get the peptides, and then you can run the peptides on LC-MS, and each peptide is quantified individually as it elutes out as a function of time, and you can walk down the chain of the peptide to figure out what the identity of that peptide is. Well, Smith's lab works with an approach called shotgun approach. So instead of isolating out each one of the peptides, he takes an entire cell, digests the entire cell with an enzyme like trypsin, and now he separates using a very high resolution separation and a high resolution mass spectrometer. His separation runs take 10 hours long. But there are literally tens and thousands of different peptides that are co-eluting in here. And he's got an instrument that's capable of detecting all of those simultaneously. So in just this example of one run, there's over 3,000 different proteins that were 100% identified in the analysis of one run. Because if you've sequenced the genome of something, you know what proteins can be coded by that DNA. We can predict the amino acid sequence, and if we can just see two peptides that match that sequence, we've got enough confidence that we can identify that protein. So all types, nucleus proteins, cytoplasm, mitochondrial, all different types of things, and you're seeing them all at once. The way that we usually do these is we would isolate some section of the cell, and we would try to analyze that and then commonly that section is going to go with 2D gel chromatography. The shotgun approach offers the potential to, if you've got high enough resolution to see everything at once. The disadvantage to this type of a technique is the amount of data that's introduced by that. He's running into a high resolution FTICR mass spec. That's his prototype instrument was named Mother, and that came from a slang word because of all the data that it produced. But it was the reasoning behind where RAID data systems came for writing computer architecture systems to write simultaneously to multiple drives. In one that's 600-minute run, they're producing 50 terabytes of data. So a large hard drive today is a terabyte. They're filling 50 of those up. I mean, literally, if I go through and start looking at those, a segment of a couple of second time slice and analyze all the peptides in each one of those, that would take years to look at all the different pieces of data in there and try to figure out what each protein is individually. So that's introduced a whole new field of the combination of computer data analysis and a terminology called bioinformatics. This is just one application of bioinformatics. But the bigger term is big data. We've got all this data. What do we do with it? And how do we make sense of it to improve human health? And we've got the point now where we can collect more data and we know what to do with it. That's where it's going to take the combination of computer scientists working together with the medical experts in the field or the different processes in biology and the different analytical and instrumental chemists to produce new data. The goal is that in the future in personalized medicine, every person could have their DNA sequenced, which you can get done now for a couple of $1,000. And then you can know what medicines are going to work for you. And if we go beyond the genome, you can start looking at the proteome, looking at the proteins, and try to figure out even more details. What cancers are lurking in your body as precursors, and how could we prevent those from ever happening? There's a lot of promise in medicine for the future. The downside to it is that future is not cheap. And when we talk about medicines for the masses, how do you make it available for everybody? I don't know if y'all have been following, and one of the things that's in Europe right now is Britain has, is it Britain? It's France. Who has the child that's, I think it's Britain.
I think it's
Is it the UK?
the three parents.
Yeah, the parents, he's been declared an incurable disease. There is a potential treatment in Italy, but the UK won't give the child a visa to go to get the treatment. They says he has to just die in the UK. So it's been a big international, and the parents are fighting it. It's been to their Supreme Court 3 times, and it's every time they've come through and said, no, it's not. They say it's endangerment to the child moving, but you're giving him a death sentence if you don't move him. So things like that are going to be becoming more and more common to our society, and what people understand and don't understand are going to be the difficult things we have to do. Okay, that was a very rapid overview of HPLC. What kind of questions do y'all have? Or I'll just hit stop here.
I get it.
Right, powerful technique found in every lab. So it's worth your while to the lab